So as promised, the version 2 of the paper is out, 2 minor mistakes and circuits corrected, a paragraph discussing KQ added. I'm not so sure what KQ is, but we'll take a look at this, and basically that's it. And yep, that is part 3 of the video coming up today. We left basically, this is the newest version, and we basically last time left here where we implemented the ideal version of the proposed circuit, and basically what's next, I think we're getting in. So basically, remember that's a just as a refresher for myself as well, that's a circuit implementation where the idea here is to find the max cut solution, right? So you've got basically one register up here. Sorry, so this line is dividing. On the top, you've got like one register. This is where you are going to where you're encoding the input, and where you're also basically doing the amplitude amplification part, which is that part in here. You've got another register down here. That basically these three qubits in here are your accumulator. Sorry for my pronunciation. The idea here is that the Oracle. So these 3 qubits are used within the Oracle to kind of count basically for each element in your superposition. So for each possible solution, actually, the amount of cats that there is. And this is where, inside these boxes is where you encode the actual edge checkers, or where you really want to check whether there's like a cat or not. And then that little guy here that controls that is basically flipping the phase of the elements that are in this particular implementation that have, I think, like two or more cats, and this is something that you in the way the algorithm is described in here, you got to repeat that number 2 that I just said. It's something you choose, is t, and so basically you keep increasing that until you find no valid solutions. And this means when you find no valid solutions, or then you decrease t, and then that means that is your max cut. The solution before you got no valid solutions is the max cut. Yeah, and exactly. So we just this was just a little example. That's the one that is mentioned in the paper. So now the trick here is so we went through these. Grover algorithm to solve the max cut problem. That's what I just described now, and that's basically the little example that we implemented. SAP Oracle, the Oracle operator. It was interesting to see how the uncomputing is necessary, so you can kind of then really execute the actual Grover algorithm, the actual amplitude amplification. I have no specific words to explain why, but the idea is if you don't uncompute, this basically 2 registers are entangled, and I believe that's the reason why then amplitude amplification doesn't work. It confused me a bit, that part here that they talk about a complete circuit implementation, and they sort of drop in here 5 qubits. But let's go ahead. So approximate a Grover search for max cut, and I think that's where we want to start. So there's a bit of math coming up, and then we've got some. I think here's where the interesting part starts, right? I think we already proposed the method for the CX gates. Yeah. So basically that subsection B is just saying that building it this way it's too expensive in terms of error. So errors and amount of control NOT gates are needed and stuff like that. So now now let's start with this. So the approximated Grover search for max cut. In this section, we describe Grover's algorithm using phase subdivided Oracle operators instead of the conventional 0 and pi. Okay, let's process that for a second. So using phase subdivided Oracle operations. instead of the conventional 0 and pi. So I guess what this means is instead of just rotating 180 degrees, which is pi, to flag, it's some sort of maybe like a divided way of doing that to maybe reduce the errors. I don't know. By using this method, we can remove the others. By using this method, we can remove the others. So this is about simplifying the circuit. So it's about having less control node operations, it seems like. So by using this method, we can remove the others used in the previous section and reduce the circuit length significantly, which is obviously good because then it means you've got less errors to worry about. We also propose a diffusion operator implementation that requires fewer control NOT gates for an actual processor design by using relative phase Toffoli gates. What are relative phase Toffoli gates? We described those methods and the verification of the effectiveness for the max cut problem. So there's a couple of references in here, 16 and 17. Just I'll go back to this quick. I just wanna that cross check just what are those papers about. I'm not sure if this reference. Trying to Deutsch Toffoli gates. If I download the paper, so what is it? So what's the relative phase Toffoli gates. Relative phase. Okay, it doesn't seem like that's the naming in here. I just wanted to quickly check whether that's something. This seems to be elementary gates, but this would be a paper about gate implementation or gate decompositions. It's from 1995. We show that a set of gates consist of all 1 qubit quantum gates and 2 qubit. Okay. Composition of these gates. Yeah. So it's basically a way of decomposing gates and stuff like that. Okay. We'll see if we need the reference. Basically, Oracle circuit design using subdivided phases. In section 3, storage of the evaluation value k, the number of cut edges, and its calculation using others, led to a large increase in the number of control X gates and occupied the largest portion of the whole circuit. So this is basically that thing here, which now of course is packed into one black box, but it's this is way bigger than that. Can I get back my version without that? I don't know. I don't think I can. If I go check my bookmarks, workspace, SAP Oracle, maybe. Let me take a look. So I might have that, because if I have that, then I can also. No, that's the SAP Oracle. It was a combination of those, and then I mean that is indeed this plus one here is again a simplification, right? So if you really want to implement the other here, it's a bunch of control nodes. So it's not just one plus one gate or something like that. That's a quirk thing. Anyway, let's go ahead. Therefore, we propose a method to express the evaluation value by the number, and by evaluation value, we're talking about the number of cut edges. Okay, so by the number of subdivided phases. In the max cut problem, we use the same data structure for node color in section 3 and unit phase, where this denotes the number of edges in the graph. Okay, so it seems like instead of using others, we're going to use phase rotations to encode that. So basically, if the I don't know, right? But it's a guess. So it's if you're okay, yeah, and it seems like this is the so you're applying a relative phase that's a function of the amount of edges. Interesting. For the cat edge determination, we introduce the following SAP Oracle using O prime or prima S sub S using subdivided phase. If an input has a cat edge between vertices A and B, then we add the theta angle to the phase information. Similarly, based on the whole Oracle operation, the best answer input becomes as follow. So let me try that quickly before I go forward. So what you would do something like, so you would probably, I'll start with a clean quirk. So let me, so you would probably do something like, so you've got your superposition here. I should get used to maybe, oh come on, start with like a clean state. I think it's a bit more real. So get into superposition, and then basically what you want to do is, as a function of the amount of cats in here, you want to rotate the relative phase, correct? So you need another qubit, which is going to be in state 1, and so you need basically, yeah, so that's the way that we're using it. So we're saying you can check these two like that, and then if it's a 1, it means that we're adding a 1 here. So this is the cat checker implementation. So if we are checking between these and for example say between these, right? So we're checking between these 2 qubits and these 2 qubits. The 0 and 1 and the 1 and 2, so to say. So what you want to do here is, in between, you want to have so you wanna rotate the phases, but then the angle that you choose, it's denotes the number of edges in the graph. G. So this is pi. So let's say if we've got 2 edges, right? Then it's pi divided by 2, the rotation you're adding. If you've got 2 edges to check, and in this case we've got 2. We're checking 2, like we're assuming, you know, that is encoding. That part is actually encoding the graph structure itself. So we're assuming that there's 2 edges. I could add another one, right? So I could probably, let's do that. So I could say, let's check these, right? So let's check between this and this, there's another edge. So now all I'm saying is and now I got 3 edges. So the angle I should rotate by is pi divided by 3. So I should probably add a custom rotation that's pi divided by 3, right? No, what am I doing? How can I? Exactly. So, and I need another one in here, and I need another one in here. So what I'm basically doing now is, okay, so I'm saying here, for example, we've got all zeros, right? Like forget the qubit, the qubit that's used, the ancilla qubit, that's the number 1 there. So 0, 0, 0, 0, there's no cat in here, so there's no rotation. There's 1 cat in here, so there's a phase rotation of 16.99 degrees, which I'm assuming is pi divided by 3. Here also 1 cat, here also 1 cat, here also 1 cat, 1 cat, 1 cat. Wait a second, but then, is there any solution with 2 cats or what? There should be a solution with 2 cats. That should have 2 cats. Why is it 16? So here is like 1, 0, and 0, and 1. doesn't seem it's rotating. Maybe it's the fact that I'm reusing the ancilla qubit, so I should just for the sake of testing that. If I do it like this, no, I get the same. That should be like that. But then that should add, so if I check the amplitudes in here, so here we're checking the first edge, so it adds only. Okay. It's actually been adding stuff. It's just that it kind of gives the full round. That's weird. Maybe it's yeah. So this is adding basically for every possible solution where there's like a 0 and a 1. It's adding that minus 171 rotation because it's pi divided by 3 is these, okay? And so when I move it, so if I do that, pi divided by 3, but that should be smaller than pi divided by 2, right? So I'm a bit confused right now. And pi divided by 2 is basically, so if I say pi, why? So I'm a bit confused now with how this is working. So but is this to give me the effect that I want? I mean, that is definitely what you want to happen here. Is that's exactly this. Pi divided by 3. No, why? Pi divided by 2. What is this weird thing? Let's see. Let's go ahead. It doesn't seem to rotate the way I want it to rotate. Maybe I'm missing something in here. So if this is a 1, right? So if the control knot makes this a 1, it means there's either a 0 1 or a 1 0, and so then you want and then you want to oh, I know, but maybe wait a second. I shouldn't reuse the ancilla qubit, that's for sure. I for sure shouldn't use the ancilla qubit. Actually, I'm stupid. I'm really stupid. What am I doing? I don't even need the ancilla qubit. I mean, if it's a 1, then you just can rotate the thing. Right? So and you could even compress that more and say that's just a control Z rotation, now that I realize. Or could you? But still the rotations are not like, that's not what I expected. Maybe because by amount determined by a formula, maybe that's the wrong. Maybe that's the rotates around Z by an amount determined by a formula. rotates around Z by an angle in radians determined by a formula. Maybe that's what I should be using. Because maybe that is... Because that is maybe in degrees, or what? So pi divided by 2 is 90 degrees. So if I say 90, or if I say... that maybe includes... that's confusing. So it's the portion of... So if I do a 1 is the Z, right? Exactly. So if I do 2, it's basically the whole thing. Okay, so this is just, you don't put here pi. You're here just rotating to use the Z Gates exponent. Okay, so you should basically do like that. Okay, so now we got it. So and this is just an auth in this case. You don't need an ancilla qubit, obviously. And so it's rotating. Okay, but in this case, it should be pi divided by 3. So it's rotating that. The 60 degrees basically for all those solutions where there's a cat. And here, I don't like that. That shouldn't rotate in this case. No, actually I need the ancilla qubit. Sorry, because that's definitely not what you want. You are otherwise just going to rotate in the cases where you've got like a 1-1. But now, okay, so now we got it. No, it's also wrong. Wait a second. I'm measuring this in the wrong place. Am I? Question here is, that's correct, but I can't just put it here because it's... No, I can put it here. Oh my god. Yeah, that works. Okay, but I should measure at the end because that's that and compute is important here. So this is basically doing the rotation in those cases where there is one cat. And now I can get rid of this, I can get rid of this and copy that. Copy those gates in between. And we don't need an ancilla qubit. So at the end, you've got all these rotations piled up. What if I just remove these? What if I just remove these? So what do I have here now? Because I think that's easier to see now, because with the additional edge, it's more complicated. But here you've got one cat, right? So 60 degrees. Here you've got two cats, so 120 degrees. Makes sense. One cat, 60, 60, 100, 120, 60, and 0. Cool. I think that's what they want to do, basically. It's my guess, but that's the way I understand that. So it's a pretty neat way to get rid of that, of all the control X operations. Although, I mean, anyway, I mean, okay, because you don't have the adding, you don't have the half adder. Okay. So you're getting rid of 3 qubits because you're not in need of an accumulator register, and on top of that, you don't need to add stuff. So that's all you need, right? Okay, if an input has a cat edge, then we add the angle. Similarly, based on the whole Oracle operation or primer, then the best answer input becomes as follow. Okay, so wait a second. Yeah, so the best answer is the one that rotates the most. But k times the angle cannot exceed pi. We next discuss the validity of theta and how to find the optimal subdivided phase. Okay, so now there's going to be a bit of math in here. When the given graph is a tree for a connected graph, the average value of the added phase after applying the above Oracle is this. I'm just reading through that right now, okay? So we'll go back to these kind of justifications later. I'm just interested. I'm going to assume that that is correct. I just probability amplitude after diffusion execution becomes this. Wait a second, but actually that's pretty neat because Ah, wait, because that what that's interesting. I mean, it's what is just going through my mind right now is, would this imply that if you run, like, what happens if I now run on the diffusion operator right away? Like, is this gonna find with higher probability the items that have the the biggest accumulated phase? Because in theory, that's the reason why you're using that, is that the reason Grover works is that it's finding exactly that pattern within your superposition that is not matching the how to put it in words. It's so complicated to put that in words to make sure I don't say something that's too fuzzy or not right. But the fact that you're applying a pi rotation to 180 degrees rotation to the solutions that you want to find, that's what allows you to then, with the amplitude amplification, basically find those elements. Now, I think that the way the paper is going to go about it is that you're going to need a bit of a different amplitude amplification, because you're going to need to, like, if you realize, if you find that k is 2, then you need to have an amplitude amplification operator that filters that pattern. I don't know if that's it, but basically, I mean, what would happen if I do that now here? So I put basically a bunch of Hadamarts. I put the X gates. I put a controlled Z, and I put again all the, I'm going to duplicate those things. I put again the X gates here and the Hadamard gates here. So it seems like, okay, so it's definitely finding the solutions with two cats. That's cool, but it seems like the 111 and 000 are also in there, which you don't really want. Okay. But those solutions are in there with higher probability. It's like the other ones are not completely, from an amplitude perspective, they're almost zero, but they're still in there, right? Okay, that's interesting, because so maybe by tweaking that, what if I would put here exactly that rotation? Nice. Okay. I mean, it's not that this might be just not the way that it's supposed to work, but it's giving me those solutions with a way higher probability than the rest. 30%, 30%. It's pretty cool. Okay. But I'm not so sure if that's the way it's supposed to work. Haven't read the rest yet, but I just like to experiment a little bit upfront. Okay. So if V5, the Oracle adds the phase to correspond to max cut, and the probability of finding becomes this. We can maximize the amplification factor by adjusting the subdivided phase. Maximize the amplification factor by adjusting the subdivided phase. Then maximize. After diffusion becomes this. Okay. We can maximize the amplification factor, then maximize P and an optimal. I don't know if So the amount of amplification depends on the difference between the average value of the added phase. Therefore, the probability of the worst solution that does not cut any edges is amplified similarly to the proper max cut solution. That's why I was seeing there. That's why I'm seeing here. If I basically just take a look at it, if I basically replace that with a Z, that's what I see those solutions being amplified as well. Why? Because the amount of amplification depends on the difference between the average value of the added phase. Therefore, the probability of the worst solution that does not and EH is amplified similar to the proper max cut solution. I need to reason a bit more about this, but that matches my results. On the other hand, since the average value increases as the graph becomes denser, the worst case probability becomes larger than maxcat. Despite such drawbacks, this algorithm requires many fewer gates than searching for an exact solution. Next, we show a specific implementation method. That's interesting. Okay, so I'm going to leave it here for this video, I think. I need to let that sink in a little bit and then re-reason that. But this is exactly what I'm experiencing when if you take a look at that circuit in here. So you see that the worst solutions get also enhanced. The amplitude gets also amplified. And this is justified by, because I think the thing here is, it's using the Grover's interpretation of the inverse about the mean. I think that's the way it's called. But I wanna okay, so I wanna try to, what I will do is I basically want to try to, so I want to try to understand a bit more. That's gonna be tricky because of the phases like that. So I've got a video on Grover where I sort of analyze the thing from the sort of an interference perspective, where I say, if you would have like the phasing in here, no, the phasing in here, right? The phasing you're doing within your Oracle, because that's your Oracle. It's almost like you could think of it as you're adding components into your superposition that then they have that like a they have a sort of a destructive interference pattern, but then when you're applying the amplitude amplification, that reverses the whole thing, and it turns it into a more powerful like creative interference. That's really badly explained, but I'll try to put the link into the description as well of what I mean. And so I want to take a look at it from those terms. But I like, you know what I mean? Like if you've got like 0, 0, 0, 1, 1, 0, 1, 1, and now you're kind of phasing like if you're phasing that solution, right? The way you're doing a way to see that would be that you have your superposition, and the phasing kind of equals to let me change color. Adding like those two negative components, so there's destructive interference, and then you get that, right? And if you think about but the interesting thing is, if you think about that particular point in time where you've got your superposition already phased, right? But I'm not going to write it as in the final interference result, but I'm gonna write it as like this. Let's assume that's kind of your mix up of possible outcomes. And now you're basically applying the amplitude amplification. What this does, is basically turn. And this is going to be a bit of a stretch. If you don't understand, if you don't grasp that, just go take a look at my Grover series, because it's a bit of a stretch. But what this does is actually invert the sign of this superposition. Not invert the sign, but basically, what was it doing? I mean, well. Effectively, yes, effectively that's exactly, I think it does something like that, where you negate everything. Could it be, or something like that? Because if you apply the Hadamard layer first, that turns into a no, that's going to be tricky to show here. I gotta go back to the video actually, but the idea is that amplitude amplification, it basically turns that into a minus, something like that, and so you're having now a creative interference where that particular solution is being amplified. Something like that. And so my wonder here is, this is where you've got like a clean superposition where you basically are phasing by 180 degrees. So this minus here, it's nothing else that like, that relative phase of like pi whatever comes up here in the exponent, right? But if you don't have that, if instead of that you've got like a this thing here, e to the power of I 4 times the angle, right? Pi 4 times the angle, something like that. You want to have you could think of designing an amplitude amplification that taps into that and basically creates the same type of creative interference. I'll see if I could, maybe I'll try to do that in my next video. I don't know. It's maybe pointless, but it will just help me validate once more my interpretation of Grover's algorithm this way. So we could do that, or I don't know, or I could finish up the paper first and then do that. But basically, that's where I'm going to leave it here. So as you can see, that is something that I can also see, that I can also kind of experience. And we're going to dive. Okay, so next comes the implementation of the Oracle. Maybe we'll go through that first. Okay, maybe let's go through the paper first. Let's stick to it, and then at the end I'll see if we can design a different whether we can design a different amplitude amplification that actually taps into the fact that you're having those this proportional phasing as a way to encode the amount of cats that you have. But that's really nice. That's a really nice that was a really nice section. It's a really interesting, really well written also. It's really interesting to see the thought process of, that's the ideal solution. That's then that's then one step farther. How would you implement that so you kind of get rid of the others? That's interesting. So let's go then through the implementation of the Oracle in the next video. Perfect.